So good morning, good afternoon, or good evening, dear attendees, depending on your time zone. So we are now 1 minute to the start point of our session. My name is Dragana Nikodinoska. I will be your chair today of the renewable energy session, and both other speakers should also be here in the session. So far we have 11 participants. There are around 40 people who have registered for our session, but let's see how the turnout develops as we go along, I guess. I hope everybody could hear me well. So in case someone doesn't, yeah, it's now 9 a.m. sharp. So I will start sharing my screen. So the title of my presentation, the first presentations for today's session, is short-term solar photovoltaic and wind power generation forecasts using the elastic net in time varying forecast combination. This is joint work with two of my colleagues at the Brandenburg Technical University in Cottbus, Germany. Allow me to start with a brief agenda of what's going to follow. I will start with the research question and motivation. Then I will briefly describe the data and the data pre-processing technique we use. Then I want to outline the methodology in order to arrive at our empirical results, and I will end up with some conclusions. Here is our research question. So forecast combinations in the field of renewable energy. Forecast solar photovoltaic and wind feed-in forecasts with as low as possible forecasting errors. That is the goal of our research. In order to achieve that goal, we want to apply the elastic net methodology to obtain forecast combinations for PV and wind data. Why is that the case? So meta forecasts are proven to be superior to individual forecasts, and also the elastic net methodology tackles the issues of multicollinearity between the individual forecasts. Our main research question of interest is whether such combined day-ahead PV and wind forecasts are outperforming whether they are outperforming the benchmarks such as the individual forecasts and benchmarks such as the simple average. So what is the main motivation? Net electricity generated from renewable energy sources in Germany has increased from 19.2% in 2010 up to 46% in 2019. The precise renewable energy feed-in forecasts aim to reduce the uncertainty related to these variable energy sources and to ensure system stability, especially when we have an increasing share of renewable energy sources in the system. Renewable energy sources feed-in forecasts are used by first and foremost PV and wind plant operators in order to minimize the deviation between forecasted and produced energy. Also, system operators are among the main users. They use the forecast to determine the reserve requirements and to manage their balancing groups. The traders are also using the forecasts in order to optimize their trading activities. So now we have come to our data. The PV and wind data for our research is obtained in cooperation with 50 Hertz, one of Germany's transmission system operators. In the control area of 50 Hertz, we can see it in yellow here on the map, approximately 1/4 of total PV installed capacity could be found, and approximately 1/3 of total installed wind capacity in Germany. So having precise forecasts in this control area is of particular importance. The data covers the period 2012 to 2018 for PV and 2010 to 2018 for wind. The data is gathered in quartered hourly intervals, totaling approximately 245,000 of PV realizations and approximately 350,000 realizations of wind feed-in, and this is measured in megawatt. We also have data on the day-ahead PV and wind forecasts at 9 a.m. as it is provided by the 6 or 7 different forecast providers. Those variables are annotated F1 to F7. We also have an additional benchmark, which is a combined forecast by 50 Hertz, and this is K, here denoted with K in the case. Now this next slide shows the PV data structure for the years 2012 to 2018. Here HRPV is the realization of the photovoltaic feed-in. K stands for the combined forecast by 50 Hertz. F1 PV to F6 PV include the day-ahead photovoltaic forecasts as provided by the 6 different providers. Here, dark blue indicates that the data is complete for the whole year, and the light blue indicates that the data is only partially available. As we can see, we start off with 2 individual forecasts in the year 2012. The number increases up to 5 in the year 2016. However, by the end or by 2018, the number is reduced to 3 forecasts. Next, we can take a look at the wind data structure. So similarly to before, HR is the realization of wind, K is the combined forecast by 50 Hertz, and F1 to up to F7 are the individual wind forecasts. With wind at the beginning, there were 4 available forecasts for the combination. The number increased to 6 in 2015 and 16. And by 2018, we are back to only 3 forecasts. So as we can see, the data structure is not stable and is changing throughout the period of our analysis. So that is one of the main motivations for using a dynamic model and also for resorting to dynamic data pre-processing, because we also encounter various types of errors within our data. Now we would like to have a look at the precision of the individual PV forecasts. On the left-hand side, y-axis, we have the RMSC in megawatt, and on the right-hand side, we have installed capacity also in megawatt. So we can see here that the largest root mean squared error is observed for forecast 3 in 2017, the gray here. But the most precise forecast actually is F2 throughout the period, and it is here denoted with orange. As we can see, the errors maybe are slightly improving, but this is very difficult to catch up with 40% additional installed PV capacity during this period. The next slide shows the individual forecasting errors for wind. So here the worst forecast is forecast 4 in the year 2010. Here F5 is actually the best individual wind forecast, denoted with darker blue. Now we have arrived at the dynamic data pre-processing step of our methodology. So we pre-process both the day-ahead forecasts, so the 96 values in step 1, and we also pre-process the historical forecast data, so approximately the past 165 days or 15,780 observations, and this is step 2. Due to time limitations, I have here represented only step 1 of our algorithm. So we first check forecast I for day d+1, and we check whether the number of impossible values is 0. If this is the case, we continue downwards. If this is not the case, but the number of impossible values violates certain criteria we have predefined here, then we can go out and we will disregard forecast I both in the estimation and in the combination. Next, we also check for the number of repetitions of zeros, and we also check for repetitions of values. And if we proceed down, we also check the number of NAs, if it's also 0, or if this specified criteria is violated. If the number is 0, we continue on. So we interpolate the impossible values and the NAs, and we go to step 2, where we check the historical forecasts data quality. So now we arrive at the methodology we use for our research. This is the elastic net model. For those maybe not so familiar with it, it's a type of regularization. When we have highly correlated predictors, one impossible or one important task is to decrease the model's complexity, so to deliver a parsimonious model and to reduce the multicollinearity. So here comes the process of regularization or shrinkage, which is to shrink the estimated coefficients, which leads to lower variance at the cost of introducing some bias. So the overall process is beneficial for the model predictive performance, as shrinkage usually reduces the forecasting errors. So the elastic net model is a special form of regression. It offers a trade-off between the lasso and the ridge regressions. And one important characteristic is that the elastic net model prevents overfitting. On this slide, we can see the objective function of the elastic net. So here betas are the optimal model coefficients, the phi t tilde are the m different individual forecasts, and the ft are the associated realizations of PV and wind power. We have here this additional penalty term. If we have lambda set to 0, this penalty term disappears, and we are basically back to a simple ordinary least squares estimations, where we minimize the distance between the realization and the forecast, so we minimize the square distance. But in our estimates, we find that lambda is statistically significant different from 0, so we have this penalty term, which is, as I mentioned, a combination of the lasso and the ridge penalties. So we resort to dynamic forecast combinations, and we apply a rolling window estimation approach. So the combined meta forecasts of phi t tilde consists of the individual forecasts phi I t tilde I1 to m at time t. So the individual forecasts are combined through the beta coefficients, or also called the combination weights. So the determination here of the combination weights is based on historical information available up to the time point t less than t prime here. So we consider the history up to 9 a.m. And for the next day, we move the rolling window by 96 values to the right, and we re-estimate the coefficients. So basically the combination weights are estimated daily, but throughout the day they remain constant. And now we arrive at the empirical results. So here we have the forecast accuracy at the yearly level for the photovoltaic forecasts for the years 2012 to 2018. The table also includes the average feed-in in megawatt, as well as the average number of used forecasts in the combination. So here delnet is the forecast, the meta forecast obtained with the dynamic elastic net method with dynamic data pre-processing. SA stands for the simple average forecast combination, in which each individual forecast obtains equal weight in the combination. So if we have two forecasts, for instance, each of them will have weight of 0.5. K here is denoting the combined forecast by 50 Hz, and F2 is the best individual forecast for PV. Here we can see that RMSE delnet is lower than RMSE of both SA and K. And it's also even better than the best individual forecasts in all years. So it averages 245 megawatt throughout the whole period. Here I have to mention that in 2018, Kai is slightly better than delnet in terms of forecasting performance. But overall, delnet achieves 13.4% improvement over the simple average and approximately 7% improvement over K. Now I would like to discuss the wind forecast accuracy at the annual level. So for the wind, we have the years 2010 to 2018. Here again, delnet is the forecast obtained with the dynamic elastic net with data pre-processing. So RMSE delnet on average is 611 megawatt and lower than RMSE of SA, as well as RMSE of F5, which is here the best individual wind forecast. So the delnet forecast achieves an overall 8% improvement over SA and 3.6% improvement over F5, the best individual forecasts. So we can conclude that the delnet really performs well and outperforms all three benchmarks which we have considered, two of which are combination forecasts and one of which is the best individual forecasts for both PV and wind. Now we have arrived at the conclusions. So forecast combinations with the dynamic elastic net with dynamic data pre-processing. Delnet is outperforming the simple average and the best individual forecast benchmarks for both wind and PV, as I already said. So the delnet of the PV has RMSE, which is 13.4% lower than that of the simple average. Delnet of wind has RMSE, which is 8% lower than that of the simple average combination for wind. Additionally, the delnet forecasting model has been successfully applied to both PV and wind forecasting and could have a much wider use for individual power plants, for smaller grid areas, and also for systems, regions, and or other countries. So with this slide, I want to end the presentation. Thank you for your attention and open the floor for discussion. Here are some references.
Hello, Dragana.
Yes.
Yeah, just a quick, Anastasios here, just a quick question. Do we have any idea whether it's like what is it that's leading to this better performance? Is it the data pre-processing more, or is it using the elastic net? Within the elastic net, is it more from the lasso, or is it more from the L2 penalization? Can we break it down where the forecasting performance is coming from?
So, for instance, we have also done the estimations without the data pre-processing step and with the data pre-processing step for both wind and PV. And we can see the differences. So we can see by how much actually the data pre-processing is contributing to a better performance. This is the case for wind because the wind data set in our case is more troublesome. So we have like a much, or we have rather a large effect of the data pre-processing on the performance for wind. But of course also the elastic net contributes to the better performance in comparison to the OLS estimation. But we also tried, for instance, just to do a lasso estimation or just a ridge estimation, and we have concluded that giving like weight of alpha of 0.5 optimizes the result. So we will need this trade-off between the two estimation techniques in order to derive superior results.
Thank you. Thank you.
Yeah, I think we slowly have to move on to the next presentation. Maybe if there are some leftover questions, we could take or discuss them at the end of the session. So the next presentation comes from Veronika Nitka. She's a student at the Wrocław University of Science and Technology. And please rate her presentation since there is a award for best student presentation. So
Hey, Dragana, I think you might need to share your sound so we can hear. We're not getting any sound.
okay, sorry for that.
when you do share your screen, Dragana, when you do share your screen,
Okay.
there's a button down the bottom that says share sound as well. So that's what you need to do. So try and share screen again.
Mm-hmm.
Oh, stop sharing and reshare. Yeah.
Mm-hmm. Yeah. Ah, yeah. Sorry for that.
Oh, that's all right. Good.
I hope nobody is able to hear.
Today, I would like to present our joint
Yep, that's
work
good.
from the Wrocław University of Science and Technology, which deals with improving fundamental variables forecast in the electricity market to help with forecasting the electricity prices. In our research, we put ourselves in the situation of a small renewable energy producer. This is a small company who does not participate in the market directly. Instead, they use the services of some trading company. Because of this, they cannot negotiate the market prices. They have to accept what they are offered. However, the decision they are allowed to make is which market to trade the electricity in for each hour, whether they want to sell their generated electricity in the day-ahead market or in the intraday market. The questions we asked ourselves in this research is, first of all, whether we can successfully forecast the spread between the prices at these two markets, and through this forecast of the spread, whether we can use it to help the company make this decision which market to sell their electricity in, and thus increase the company's profits. Our research published already in Energies answered these two questions, and the answer is yes, we can actually forecast the spread, and we can use this forecast to increase profit of such a small company. And now we are asking ourselves if we can do even better, if we can improve upon the publicly available TSO predictions we used previously by using our own models, and if it is possible actually to improve upon these predictions, what can we gain in terms of profits if we can improve the outcome even more? Data we are using in this research comes from the German market, and it's the prices from the two markets. They had an intraday marked as DA and ID respectively. Also, we have the three fundamental variables: the load, wind energy generation, and solar energy generation, and also the publicly available forecast published by the transmission system operator, marked with similarly but with Fs. The time paths of our prices are shown in this slide, and as is customary to the electricity market, we see multiple spikes, and in the German apex market, we have both positive and negative price spikes. This is the price in the day-ahead market. In the intraday market, they are highly correlated. However, when we look at the third plot, which shows the difference of the prices between those two markets, we see that there are quite a bit of spikes and differences, and this is what we are hoping to forecast and hopefully gain some money for our hypothetical company. I can also show the time paths of the fundamental variables, the load, wind, and solar, all of which exhibit some randomness and yearly seasonality. So we can define our decision by setting up a random variable y, and we set this random variable to 1 if at day t and hour of the day 8 we sell in the intraday market, and otherwise we set it to 0 if we decide to sell the electricity in the day-ahead market. And selling in the day-ahead market is the most obvious basic choice a company can make, and this is why we take it as our benchmark strategy. To it we will compare our results to. However, our aim is to make a data-driven decision, and in this case we define this variable y to be equal to 1 if we predict the price in the intraday market to be higher than in the day-ahead market, and therefore it is profitable to sell in the intraday market, and we sell in the day-ahead market if our models predict otherwise. So to know the value of this random variable, we need to have the forecasts of the market prices. And here I present the model for the day-ahead market price, which is a linear autoregressive model. It consists of an autoregressive component with 3 different lags, daily average, minimum, and maximum price from the previous day, also the last known price from the previous day at midnight, the forecasted values of the fundamental variables, dummies representing weekdays, and random noise. When it comes to the intraday market price models, we have 2 variants. And first of those variants is very similar to the day-ahead market model. However, because not all intraday prices from the previous day are known at the time of making this decision, we substitute the unknown quantities like those daily averages and some of the hours with their respective day-ahead market quantities, which should work reasonably well because they are very highly correlated. The second approach, which we denote as the ID2 model, to differentiate from this ID1 model, is using known in the literature fact that a major driver of intraday market prices are the forecast errors of the TSO forecasts. And here we, in this model, is dropping the most of the autoregressive part, instead taking the errors of the fundamental variables. And here we use the X to write more compactly all the matrix of all 3 fundamental variables, and we take its forecasts, which come from our models I will show on the next slide, and we take the differences between our forecast and the TSO forecasts for the current day and from the previous day. Our models for forecasting the fundamental variables are as follows. The most complicated one is for load, and it is very similar to the models for market prices, in which we take the forecast of all fundamentals and the daily statistics. Whereas the models for the renewable energy generation are significantly simpler, and they take as the autoregressive effects. And we validate our results through 4 different classification measures, and our predictions are evaluated by 2 classical error measures, root mean square error and mean absolute error. And when it comes to the price spread, we introduce 2 additional measures of classification power, so checking how many of our decisions, what fraction of those was correct. And also we yearly profit over the benchmark, with the benchmark being selling always in the day-ahead market. So now for the results. We have 3 distinct components to this research. And so we have divided our data into three periods of equal length. Each of those is 1 year long. We start with in the year of 2015, and our data lasts until the end of the 2017. So the first part of the research is forecasting the fundamental variables, and we take the year 2015 as the calibration period, and then we forecast for the subsequent subsequent 2 years, and we check the results. So this table shows both error measures for all three of the fundamental variables, and we compare the TSO error models, the TSO forecast errors to the errors of our models. And as we can see, our improved forecasts perform really well. This is most visible in the case of the load forecasts, where there is a really vast improvement. However, also the wind forecast notes a statistically significant improvement over the TSO. Slightly worse situation we have for the solar, where in terms of mean absolute error, it does not improve at all, while in terms of root mean square, the improvement might not be statistically significant. However, they are quite promising anyway. So we can use it to proceed to the second and third parts of this research, which is forecasting electricity prices and then using those forecasts to produce the decision based on the price spread. And here we calibrate the price models on the middle period of our data, year 2016, and evaluate the results on the last year. Here we have the table with the results for both markets and all three models, because we had 3 different models for the intraday market. We compare both error measures for the TSO forecasts and 3 approaches for the models. The first of those is the most basic model, devoid of any exogenous variables. So we don't take any of the fundamental forecasts, leaving only the autoregressive structure just to control the outcome. The second approach we call enhance is using the very forecasts we obtained in the previous step. So this is our main result. However, we also compare this approach with plugging in the real values in the models, obtaining what we would call a crystal ball predictions to see what could happen if we could predict the values of the fundamentals perfectly. And here we can notice that the second model in the intraday market performs better than the ID1 model, so I will focus on this one. And the results show that yes, we can use our fundamentals models to obtain a significant improvement over the TSO forecast, and an even bigger improvement by using the real values. However, there is quite a surprising outcome when it comes to the day-ahead market, because the improvement with using the enhanced forecasts is barely there. It's not even statistically significant in terms of mean absolute error, while taking the real values of the forecasts leads to even worse predictions than taking just the system forecasts. And knowing this, we can move on to forecasting the price spread, where we had to differentiate between 2 different approaches to this forecast. And the first one takes the prediction with the fundamentals coming from our models for both intraday and day-ahead market. However, we also considered the situation where we take our improved forecast for the day-ahead market. However, we predict for the intraday market. However, we predict the day-ahead prices by taking the TSO forecast, instead of fundamentals from our models. And I will focus again on the ID2 model for the intraday market, because it tends to perform generally better. And as we could expect from the previous table, where where the TSO forecast fared better in forecasting the day-ahead market price. The classification power is improved with this approach compared to using our models in both cases, and there is a very major benefit when using the perfect forecasts. However, we can notice that the profits do not necessarily follow the classification power. It is true for when we take the real values of so perfect predictions of the fundamentals. However, when it comes to the realistic forecasts, actually we have a better outcome by taking our models in both day-ahead and intraday markets. More research is needed to determine if this is some kind of rule for other markets, of if it's just the peculiarity of the data we had here. However, we can conclude that the errors of the TSO fundamentals forecast can in fact be reduced, and significantly so when it comes to load and wind generation forecast, with a more minor reduction for solar energy. And also this improved forecast can be used further to improve on forecasts of the prices in the electricity market, which is a very interesting topic for many researchers. However, this effect is proven mainly for the intraday market, while in the day-ahead market, still we can achieve just as good or even better results while using just the system forecast published for the generally available. But the profits we can gain by using our data-driven approach can be as high as 3,000 euros per megawatt hour yearly, which is not a huge amount compared to the total profits of a company. However, it is not insignificant, so it is definitely worth looking into. And this is all I wanted to present today, and thank you for your attention.
So we have maybe time for one question now from the audience. If that's not the case, then I will suggest we continue to the next presentation, where we have Victor Andrade from the Electricity Energy Research Center.
Hello everyone, thank you for being here, watching this presentation. My name is Vitor. I work as a researcher at CEPEL. CEPEL is a Brazilian Electrical Energy Research Center. And today we're going to talk about the models developed by CEPEL to predict the renewable energy sources. This is the title of our work, Renewable Energy Forecasting, using stochastic models to support the Brazilian interconnected power system short-term energy operation planning. This is the structure of the presentation. We had an introduction about the subject, a Ventus model, which can be used to forecast wind power, and the privatized model, which can be used to forecast swing flows, and a conclusion about the models. Here we have a map of interconnected Brazilian electricity grid. The size of the Brazilian transmission grid is about 4,000 kilometers, which basically the size of the Europe. Also, we have a large share of renewable sources, okay, mainly hydroelectricity and increasing of participation of so-called renewable sources, okay, such as wind and solar, and a relevant hydrological, temporal, and spatial diversity, okay, allowing energy complementarity among the several regions of the system. This is a chart of Brazilian electricity generation per technology. So we can see the predominance of the hydro source with almost 65% of all electricity and important participation of wind power source. So these models are developed by Sapel to guide the operation planning of the Brazilian power generation, considering the long, the medium, and the short time horizons. Okay, here are the three main programs of the planning operation: New Wave, the Comp, and the SAM. New Wave is used in long-term planning, the Comp in the mid-term planning, and the SAM in the short-term planning. Okay, and we can see that these two models, Ventos and Previvais, are connected to New Wave, the Comp, and the SAM. Okay, which means that we can use the results of Ventos model and Previvais model at the operation plane of the system. So today we're going to take a look at these two models, Ventos and Previvais, to know how they work. Okay. Now, at first, the Ventos model. Here's an overview of the model. We have a model able to provide hourly wind power forecasts uh, up to 7 days ahead. Okay. The model provides not only a point forecast, but a probabilistic forecast. We're going to talk about this very soon. And the model is based on the quantile regression statistical technique. This is the relationship between wind speed and energy production of a wind turbine. Okay, this is how we can model the response of the turbine given a wind speed. We have these formulas here that describes the relationship. Okay, but what we have in real data is this type of curve. Okay, this is not exactly what we have seen before. So, what we can estimate a wind power generation given a wind speed value with so many possible values on the power curve? Before answering this question, I want to talk about the types of forecasting. In many applications, we have a point forecasting, or a single value forecasting, or a deterministic forecasting. But we can do more than that. We can estimate not only a point, but several points of distribution of responsible variable. This is what we call a probability. So here we have an example of a point forecast. Here, this is a single value forecast. And here we have an example of probability forecasting. I am estimating not only a point, but a distribution of my response variable. And why this is important to us? Well, for example, the operation reserve must be dimensioned in order to cover the uncertainties in the load forecast and in the forecast of the power generation. Also, uncertainty can be obtained by forecasting the probability distribution of wind power production. Okay, that's it. The probability forecast. That's why we estimate a probability forecast advantage. So this is the idea. We have historical data of wind power generation and wind speed. Okay, so we can train our model to estimate the distribution of the wind power generation given the wind speed. After that, with wind speed forecast, we can finally estimate a probability forecast of wind power generation. Okay, and how we can do that? We can do that using the statistical technique of quantile regression, which idea is similar to the linear regression. As we know, in the linear regression, the regression equation provides the estimation of expected value of responsible variable. Okay, and in the quantile regression, the regression equation provides a quantile of the response variable. Okay, so if you want to estimate several quantiles, we will have several regression equations. Okay, one for each quantile. Besides that, in the linear regression, we assume a normal distribution of the response variable. We don't have to do that in quantile regression. Okay, so we can estimate any distribution. Another difference is in the linear regression, we adjust the parameters by least square method. Okay, and in the quantile regression, we adjust the parameters minimizing the pinball loss function. Okay, the idea of this function is to penalize the error with tau when the error is greater than 0, and with 1 minus tau when the error is smaller than 0. Okay. Also, we can solve this problem with the iteratively weighted least square method. Okay. Well, the climate prediction models provide to us forecasts of magnitude and direction of the wind. Okay, so to consider this information, we have to transform the polar coordinates into Cartesian coordinates. Okay, this is relationship between wind speed and power generation, as we saw before, and this is relationship between U and wind power generation, and this is relationship between W and wind power generation. U is the wind speed multiplied by cosine of the direction of the wind, and W is the wind speed multiplied by the sine of the direction of the wind. So, as we know, if f is a smooth function, we can approximate f by a sum of basis functions. Okay, for example, the b-spline functions. In the Ventos model, we use the cubic splines to represent our functions. Okay, the process to obtain these cubic splines is described right here, and basically we obtain the basis of smaller order until the basis of order 3. So we obtain the basis of order 1, and after that we obtain the basis of order 2, and finally the basis of order 3. So this is our model. We have an equation of this type for each quantile, and of course we can define which quantiles we want. So we have to estimate these parameters for each equation for each quantile. Okay, we have to estimate the regression parameters. Okay, and for each component we have to estimate 10 b-splines for each component. Okay, so this is how we capture nonlinearity present in the relationship between wind speed and power generation. This is a print of interface of the model. So we can use the historical data of power generation and wind speed and direction, of course, okay, to estimate our quantile regression equations. And after that, with wind speed and direction forecast, we can obtain the short-term forecast of wind generation, okay, probabilistic forecast. This is an experiment done with data from a wind farm at Galicia, Spain, and we can see the predicted interquartile ranges. Okay, we have interquartile range 5% to 95%, the interquartile range 10% to 9%. Okay, the line here is the median, and the dots are the verified wind power generation. Okay, so as we saw before, the Ventus model is able to predict a single value, in this case the median, uh, but also a probability forecast, the interquartile ranges. Okay, so now we're gonna take a look at the Previse model. Here's a review of Previse. Previse has in fact three models. Previse H, which provides a daily stream flow forecasting up to 14 days ahead. Previse, which provides a weekly stream flow forecasting up to 5 weeks. Okay. And Previse, which provides a monthly stream flow forecasting up to 12 months. They are based on the classical box engine theory to modern time series. Okay. Previse and Previse M takes into account the statistical properties of the stream flow series, okay, and provides the expected value and theoretical confidence interval. And the Previse H takes into account the different stream flow behavior in rising and recession periods. Okay, so the basic idea of Previse model is to select among the various alternatives of stochastic model of weekly flows the best for each week. So we test several alternatives and choose the better for each week. This is our set of alternatives. We test autoregressive models, moving average models, periodic or not. Okay, we can aggregate the autocorrelation function by period, weekly, monthly, quarterly, and annual. We use these methods to obtain the parameters, moments, and regression. Regression can be a simple regression or a regression to the average. Okay, we can transform the series using the logarithmic transformation or not. The total of alternatives is previses 140, and the prevised M is 89. Okay. This table summarizes our set of alternatives as we saw before. Okay, we test all of these models and we choose the best for each week. This is how the Previse select the best model for each week. The model uses a cross-validation procedure. Okay, first the model estimates the parameters based on the first half of dataset and calculate the error using the second half of dataset. After that, the model estimates the parameters based on the second half of dataset and calculates the error using the first half of historical dataset. Finally, the model takes the average error of the two subsets. Okay, the alternative that has the lowest average error is selected for that week. This is an example of stream flow forecasting for Tokuro hydropower plant. Here is a sample autocorrelation function of the weeks which are closest to forecast week, okay, and the forecast stream flow. We have the expected value for each week, okay, and the confidence interval. This is the Previse H. Previse H is based on stream flow synthetic scenario generation. Okay, here the stream flow is composed by two components, okay, representing basin recession and rising patterns. Okay, the component O, which is basically the basin empty, and the component U, which is basically the flow increase. Okay, The component U is estimated considering up to 3 rainfall classes. The process here is we generated 10,000 scenarios of daily stream flows up to 14 days ahead, and we choose the scenario whose the average is closer to our weekly forecast target. Okay, these scenarios will be our daily forecast stream flow. So this is our conclusion. The Ventus model provides hourly wind power forecast up to 7 days ahead, which also is a probability forecast and is based on the quantile regression technique. The prerevised model is based on the Box-Jenkins time series model and provides daily, weekly, and monthly stream flow forecast. Okay, this is important. Both models may be used for the operation plan of electricity grid. Okay, the models are in constant development, and there are some forcing studies using the results of prerevised and Ventus models on the same model. Okay. That's it. If you have any questions, you can discuss after the presentation, or you can send me an email. This is my email, or you can send an email to a Ventus model account or the prerevised model account. Okay, thank you.
So thanks also to the third and final speaker for today. Does anyone have questions for Victor?
I can, if I can pose a quick question. Which kind of software implementation did you use? Did you use some of the packages in R or Python, or for the quantile regression, for example?
I'm sorry, can you hear me?
Yes.
Yes.
Can you hear me?
Yes.
Okay, so
Could you repeat
I
the
just
question?
my name is Peter here, so I just want to know which kind of did you use some available software implementations, some package in R or Python for example, the quantum regression?
We use R to implement the models and tests, and after that we used C# to implement the models. And in case of Ventus, in case of prerevised, we use Fortran.
Okay, but did you use, for example, the Quantreg package in R?
Quantreg, yes,
Yeah.
to test our models. But after that we implemented in C#.
Okay, cool.
Okay.
Yeah, thanks a lot.
Thank you.
Okay, do we have any additional questions for other speakers, or questions for the general discussion maybe? Okay, if no one wants to jump in, I had one question for Veronica, sorry. So you mentioned that the error reductions for solar weren't very big in comparison to the wind forecasts or for the load forecasts. Do you believe that the TSOs are really using an optimized model for the solar forecasting in Germany, or what is your take on this?
So no, they are definitely not optimized, because we can show that the predictions of the TSO forecasts are biased. However, we had problems with improving upon those TSO forecasts, but I suspect it can be done. It just needs a better model than those simple ones we attempted so far.
Okay, can I ask,
Mhm.
did you
Thanks for
use,
that.
in your models, did you use additional weather forecasts and other inputs like that?
No, we didn't, because our assumption was to use publicly available data. So maybe we could use some public website with weather forecast. However, we didn't take any more involved data. So just what the TSO publishes officially, so that anyone in theory could use our forecast, any participant, without paying for another data.
But I think there are plenty of even available freely GFS and other weather forecasts. So that might be a good idea to try. Thanks a lot.
But Veronica, you use, one additional question. You use like one forecast for Germany as a whole, right? You don't look at the four individual TSOs and then make one forecast for Germany as a whole.
Yes, we took the data from transparency for the
Did you get my question
German
or not
zone.
really? Uh-huh.
Yes,
Okay.
I did. Yes, we used
Okay.
one for the whole Germany.
Good, because I'm having some internet issues, I think, at the moment. Thank you for that.
I heard you. Thank you.
Good. If there isn't anything else, I don't know, to discuss in the panel, I guess we can slowly wrap it up and move maybe to the next sessions of the conference. I think some sessions are already running. We have a packed schedule today. So thank you everyone for listening in, for participating. I want to thank once again the speakers. Please rate the student presentation for the award, and wish you a productive and successful conference, everyone.
Why don't we all
Bye
clap?
bye and take care.
We used to clap when we were like, so thank you.
Yeah, I didn't see any reactions so far. Yeah, with this virtual format, I guess is new for everyone, but thanks for suggesting this, Peter.
Bye-bye. Thanks.
Thank you. Bye.
Bye, see you
Bye.
soon.
Bye-bye.
Bye, Veronica.